Hi, today I'm going to describe a bit the library Signaali. This is a reactive library that connects signals and effects. It also can be used to compute derived data. It's a library which works in Clojure and ClojureScript, but it's important to know that it was developed specially for some ClojureScript environment, so there is a reduced support for multithreadings and concurrency in that library. Therefore, I suggested to only use it for the front end. How to get started with it? First, you can visit this website. This is a repository for the library. And then if you want to directly jump into programming, you can import this into your deps.edn and fire your REPL. So Signal is basically very similar to a Clojure atom. You can query the data inside, and you can change its content using reset and swap. From a signal, you can have derived signals. Here I have a function which calculates a new value, and I have a small side effect inside just for the purpose of the demo. Normally, inside a derived signal, you don't want to have any side effect. But here it is important to understand when the run function of a derived effect is running. As you could see, when I created the derived signal, nothing was executed. The run function is only executing when you access the data and when the data is not up to date. When I change the base signal, again, nothing happens. It's only when I read the data that the run function runs again. So those are lazy signals. Usually in a reactive system, you want to have some data, some derived data, and some effects which are triggered when those data changes. Here it's a little bit more general because we talk about signal. So resetting a signal to the same value will also trigger some updates. And here is an effect. So the effect is very similar to the derived signal in the way we build it. It has a run function. And again, it is pretty lazy, which means it's not going to run by itself. You have to ask its value, and then if the effect is based on some reactive nodes which are not up to date, it's going to rerun. But if the reactive nodes are still up to date, it's not going to rerun. So like this, you can make sure that the effects only run when it is intended. Here I am changing the value of the base signal, and let's observe what happens. Actually, nothing happens, but when I ask the printer effect to give me its return value, it runs again. Usually, we don't need the return value of an effect. We have this because all the nodes inside these libraries are using the same class. The base signal, the derived signal, and the effects are all using the same Clojure type. And the difference is what properties you give to this type when you build it. So a base signal will have a value, a derived signal will have a run function, and an effect will have exactly the same, but it will have a tag that says that it is an effectful run function. The effectful run functions are treated differently. When they are tagged as stale, they will be added to a separate list. And this is what this list is about here. We have a function that reads this list, that runs all the effects which are stale, and empty the list. So here we have no effects which are stale, but if we change the base value, we have the effects running again. There is a small variation between what is a signal and what is a state, in the sense that a state will only propagate the signal downward toward its watchers only when the new value, which is assigned to it, is different from the old value. And how different it has to be, this can be customized through the parameters. If we take a look at the option of create state, we can see here a flag, which is not in its counterpart, create signal. Create signal is here. You can see we call the function make reactive node. And here this is exactly the same, except that we have this propagation filter. It's going to propagate the signal only when the last value and the new value are not identical. If you want to change this behavior, you can call create signal with a hash map of options. From there, you can override the default behavior. So, small demo. We have a first name and a last name. Those are states. And we have a derived state. So the derived state is creating using create memo. Create memo is the same as create derived, except it has this specific flag turned on. Propagate filter fn. So we can see full name gives Alice Anderson, and then we can see that the run function happened. And if I change first name to Bob, and I ask the derived value, it's going to be Bob Anderson. And if I set it to Bob again, and I ask the derived version, what is its value, we can see that the run function did not run. So the reason why this library was made in a lazy way was to avoid some glitches that usually happen in reactive systems when a new value is pushed from the place where it is modified toward its watchers. Okay, let me describe a bit. We have B that depends on A, C that depends on A, and D that depends on B and C. And we have this small snippet here, which represents this configuration. In a non-lazy system, where the updates are pushed eagerly, changing A implies that B has changed, implies that D has changed. And then because A has changed and C is also watching A, C will change and D will change. And that's a problem because here you can see D changes twice. It's recomputed twice. So if D doesn't have any side effect, it's okay-ish because you just run the same computation twice. So you waste a bit of CPU, but there is no visible bugs. If D has some side effects, then you can have some bugs because it runs twice when actually it should run one. So in a lazy way, what we do is when A is modified, it notifies the watchers that it is containing a stale data. And the watchers are propagating it downward. So D gets notified twice that its dependencies are stale, but D does not run. It just propagates this change of status. The value of D is calculated lazily. Let me show you in the demo how it works. So here I evaluated D, and you can see that D has run. And because D is using B and C, B has run, C has run. And because of the laziness, we only evaluate things which are not up to date from the bottom up. And we only have the effects running the number of times we expect them to. This is the end of the video. I hope you found it useful. See you next time.